Mathematics is a broad field of studies consisting of branches such as algebra, geometry, statistics, and many others. In math, there are also multiple operations, formulas, and sequences. We deal not only with numbers but also variables, conditions, and statements. However, not all statements in mathematics are automatically considered true. To make these statements seem believable, we prove them. Proving has many forms, and that will be our main focus for today. Hello, everyone. I am Cassandra Cabrera from the Philippines, and today I'll be talking about proving in its many forms. Proving is something that is commonly used in everyday lives by lawyers and detectives, proving that their client is innocent or proving a case. In math, we prove statements such as the congruence of two segments or the value of a given integer. Today's discussion will consist of an introduction to proving, its main forms, and a few examples. So, what is proving? Proving in math uses theorems and postulates to prove that a mathematical statement or hypothesis is true. Theorems are statements that have been accepted as true, and postulates are statements that are automatically considered true. Proving has many forms, namely direct proof, contrapositive proof, contradictory proof, and inductive proof. Let's break these forms down. The first and most common type of proving is direct proof. It starts with a given statement or hypothesis, then followed by theorems or postulates that help arrive at the conclusion. It relies on facts and definitions to help in justifying the hypothesis. Next, we have contrapositive proof. The normal statement follows the form if A then B, given that A is the hypothesis and B is the conclusion. The contrapositive of a statement follows the form if not B then not A. We normally prove the contrapositive of a statement if using direct proof is too complicated. We also have contradictory proof. It's quite similar to contrapositive proof, but instead of proving the opposite of the entire statement, we only negate the hypothesis. When the negated hypothesis cannot be proven true, this implies that the original statement must be true. Lastly, we have inductive proof. This proof is commonly used to prove statements about natural numbers. It shows that if a statement is true for a specific value, then it also must be true for the next. Now that we're made aware of the different forms of proving, let us take a look at a few examples. For our first example, let's use direct proof. The statement reads, if a triangle has two equal sides, then it has two equal angles. We are given triangle ABC with the measures of segment AB and AC being equal. We are to prove that the measures of angle B and angle C are also equal. Given that the segment AB and AC are equal in measurements, the triangle ABC is isosceles. And we know that in all isosceles triangles, the angles opposite the equal sides are also equal. Hence, since segment AB and AC are equal, angles B and C must also be equal. Next, we have our contrapositive proof. Our given statement is if n squared is even, then n is even. The contrapositive of that statement is if n is odd, then n squared is odd. To prove the contrapositive, let n be equal to 2k plus 1. Then n squared should be equal to 2k plus 1 squared, which when simplified is 4k squared plus 4k plus 1, and when we further simplify it, we can have it in the form of 2 times 2k plus 2k plus 1, which is an odd number. Therefore, since the contrapositive is true, the original statement must also be true. We now have our contradictory proof. Our statement is, there is no integer that is both even and odd. Let's use the contradiction of that statement and assume that there is an integer n that is both even and odd. So, if n is even, then n equals 2k. If n is odd, then n equals 2k plus 1. Since n is both even and odd, we assume that n equals 2k and n equals 2k plus 1. However, 2k is not equal to 2k plus 1. Therefore, there is no integer that is both even and odd. And lastly, we have our example for inductive proof. Our statement reads, for all natural numbers, n is greater than or equal to 1 1 plus 1 plus 1 plus 1 n times should be equal to n. To prove this, let's assume that the statement is true for n equals k. Then 1 plus 1 plus 1 plus 1 k times should be equal to k. It should also be true for n equals k plus 1. 1 plus 1 plus 1 plus 1 k plus 1 times is equal to k plus 1. Therefore, by induction, 1 plus 1 plus 1 plus 1 n times is equal to n for all integer n greater than or equal to negative 1. And that concludes our examples for proving. Throughout this discussion, we've seen what the different ways to prove are, and we also get to see them in action. Proving also teaches us the importance of upholding truth. Hopefully, we not only use facts to prove statements in math, but we also use facts to help bring justice to those who need it. Again, I am Cassandra Cabrera from the Philippines, and this has been Assumption to Assertion, proving in its many forms. Thank you so much for listening.